today's machine learning crash course. Today we want to have a discussion about classification metrics as the last session in this part. So we want to talk about classification metrics. We took a quick look at classification metrics in previous sessions, but maybe it's better to have a look in a more deep way in this session, because it is so important to grasp this stuff and use them in real world applications. Okay, so actually we want to talk about in this session about ROC, which is a receiver operating characteristic, about AUC or area under curve, about recall or true positive rate or sensitivity, about precision, and about specificity, and false positive rate, and also some metrics for actually regression, mostly that actually we learned about them in previous sessions, but just for recap. Okay, and we will learn about this for binary classification. For multi-class problems, we just take a look at confusion matrix to get how much our classifier performs well. Okay, so in two class problem, we could create a matrix for our results, for our predictions. Let's say we have a matrix, and in here it is, let's say it is related to actual label. So we have 0, 1. These are means the actual label of this data is 0, and in here we have 1. And the rows are related to predicted labels by classifier. So in here we have 0, 1. If we have 0 in this row, means that our classifier predicted 0 as the label of the data in this row. Okay, so we call each of these cells specific things. If the actual label is 0 and the predicted label is 0, we call this true negative. Means that our classifier predicted truly that data has label 0. So in this case we call this true negative. But if the actual label is 1, but our classifier predicted that as 0, then we have false negative. So it means that our classifier predicted that it is a negative or a 0, but it is false, because we know that it is the actual label is 1. So similarly in here, if the actual label is 0 but the predicted label of the classifier is 1, so we have false positive, because our classifier predicted positive, but it is false because we have 0 in here, right? So actually we could name that negative and positive and false and true to get this better probably. And in here we have true positive, right? So the actual label is 1 or true, and the predicted label by the classifier is 1 or positive, so and it is true, so you have true positive in here. Okay. Okay, now we could actually define different measures to measure how much our classifier is performed well on the task of separation between negative and positive classes. So one of the definitions is recall or true positive rate, or TPR, or sometimes it is called sensitivity. And the definition of all of this is true positive over true positive plus false negatives. Okay, so the total number of true positives over true positives plus false negatives, so it means that we are getting some kind of accuracy in here, so for all the true labels. Okay, so this is recall. And also we could define precision as the true positive over true positive plus false positive. So as you could see, it is now we are working in here. So as the predicted label of classifier, we want to know how much the classifier performed well on the predicted data. So this is precision. And we could define specificity as true negatives over true negatives plus false positives. And also, don't worry if you are a little confused, you actually know how to use them, and we will get some intuition about them in a short. And we could define false positive rate as false positives over true negative plus false positives. Okay, and actually you could define it as 1 minus specificity, and the relation between these two are clear now. Okay, for getting some intuition, let's say we have when we have a two-class problem, we could plot the distribution of positives and negatives data. So let's say we have something like this. Let me to show the positive distribution data as red, and for blue we have negative distribution. Okay, let's say we have a classifier with a very high threshold. So let's say the threshold of classifier is here. Okay, so we have a classifier that it tells us the prediction based on this threshold. So if the value of the data is more than this threshold, then the predicted value is 1, and it is 0 if it is below the threshold. So if the threshold in here, actually our classifier tells us all of the data are negative, right? So because all of the data are in this region and they are below the threshold of the classifier. Okay, in this case, what is the accuracy if the data, so let's say we have 10 negative data and 10 positive data, so we have balanced data in here. If you use accuracy as your measurement to get the idea about how your classifier performs well on the data, then you probably end up, because now your classifier tells you have from the negative data, it predicts all of them true. So the accuracy will be 10 out of 10 plus 10, because for positive data it tells us they are negative or they are false, and for negative data it tells the truth, the true value, so it is 0. So we have 10 true prediction and 10 false prediction, so the accuracy is 50%. Probably you get that accuracy is not a very good measurement maybe of getting the performance of classifier. Maybe it is too incomplete to get you information about your classifier. By the definition of these measurements, we will see that we could gain a lot of more intuition about our classifier and about the performance of the classifier. So, but now in this case, let's say, what is a recall? So we know that the recall is true positive over true positive plus false positive. In this case, the classifier tells us all the data is negative, so we don't have any true positive, so it is 0. But for specificity, we have true negative over true negative plus false positive. We have all the true negatives, and the false positive is 0 because we don't have any positive predictions by the classifier. So the specificity is 1. So we could see that there is kind of maybe trade-off. We will see that in a short. If we move the threshold from here in this way and decrease the threshold, then the recall goes up and specificity goes down. So we could see the trade-off between these two. Okay, so to show the true positive, true negative, and false positive and false negative, we could see them on the plot. So again, let's say the distribution of positive data is something like this, and for negative data we have something like this. And let's say this is the threshold of the classifier. So for this data, for this negative data, the classifier predicts label 1 instead of 0 for them. So we have false positive in here, right? Classifier tells us they are positive, but the label of these data are not 1. So similarly, in here we have false negatives, and in here we have true positives and true negatives in here, right? So now we could get some kind of intuition about what is true positive, what is false positive, what is false negative, and what is true negative. Okay, for this kind of distribution of true 1 and 0 distribution of the data, if we plot the true positive rate versus false positive rate, and we have 0 and 1 in here, and let's say we change the threshold to plot this so by changing the threshold, we are changing the false positive rate. If you plot the true positive rate based on versus false positive rate, you will see you have something like this in here. Okay, so we actually call this plot ROC, or receiver operating characteristic, and it actually gives you a measure which is the area under true positive rate versus false positive rate. We call that AUC, or area under curve. So it gives you a measurement of how much the classifier performs well to separate between 0 and 1 classes, right? So to show you another case, let's say now we have the distribution. This is distribution of 0 class, and this is the distribution of 1 class. They are perfectly matched, and so this is so bad actually for us for the classifier to separate between these two classes. So if you plot the ROC for these distributions, then you will have a line for your ROC, and the AUC is this area which is 0.5. So if you have larger AUC, then you will have better performance for your classifier. So higher AUC means that better performance and separability capability of your classifier. Because to see this, actually we could have this scenario that, let's say we have this kind of distribution that we could perfectly separate. So in here we have true positive, and in here we have true negative. If you plot the ROC, you have something like this. The true positive rate jumps up to 1, and you will have something like this. And in this case, the AUC is 1, and it means that you have a very good classifier, and your classifier have enough capability to separate between these two classes. So the AUC between 0 and 1 and higher is better. So it is kind of performance measurements for you to use. But if you have so we actually saw that in this case we don't have any kind of clue that what is the actual label, because the distributions of negative and positive class are perfectly matched. And so in the worst case the AUC is 0.5, but what does it mean if we have AUC under 0.5? Means that if we have something like this, in this case actually it means that we the model is actually reciprocating the classes. Or so if this is the positive class distribution and this is the negative, if we plot the ROC, we have something like this. As you could see in here, now the ROC, the AUC is approximately 0 or under 0.5. So it means that the classifier predicts the negatives as positives and vice versa. So you just need to invert the prediction of your classifier to convert that to this or AUC. Okay. So basically, for measuring the performance of classifiers, people put y is equal to x, means that the AUC of 0.5 as the reference line, and so you want to have the classifier, this classifier is better than this one, and so on. So you want to have bigger AUC for your classifier. And so if you increase the sensitivity, then from the relation the specificity decreases, and vice versa. If you decrease the sensitivity, then the specificity increases. So from this also we could infer that if we decrease the threshold, so if we decrease the threshold, then positive values increase, right? So because if you decrease the threshold, means that your classifier introduce more positive values as the prediction label. So the specificity decreases, and so sensitivity increases. And also similarly, when you increase the threshold, you have more negative values, so the sensitivity decreases and specificity increases. They are maybe kind of make some confusion for you at first, but when you work with this kind of measurements, you will used to using them. So also we know that the false positive rate is 1 minus specificity. So if you increase the true positive rate, then false positive rate will increase. So we know that the true positive rate is actually the sensitivity. It is often when sensitivity and specificity are used together, and true positive rate and false positive rate are used together, but we know that the true positive rate is actually the sensitivity. So the true positive rate increases when false positive rate increases, and vice versa. So if true positive rate decreases, then we have and false positive rate decreases. Okay, and also we have seen this fact in ROC curve. We have something like this. We have an increasing plot, so it means that when you increase the false positive rate, the true positive rate increase. Okay. And also in the last session, we have seen another measurement that is a balance metric between precision and recall, which is F1 score, which is defined as 2 precision times recall over precision plus recall. So because there is a trade-off between precision and recall, so if you want to see the performance of your classifier with just one number and compare between different classifier or between different classifiers, then using F1 score could be very useful for you. So, and also it is important when you have a data imbalance between positive and negative samples, it is better to use F1 score instead of AUC, because actually AUC, or when you want to create ROC, it averages over all possible thresholds. So it is better to use F1 score when you have imbalanced data. And when you have multi-classes, I think the best way is to look at the confusion matrix itself. So let's say we have a 3-class problem. So you could create the confusion matrix. We call this confusion matrix. And in confusion matrix, you like that you have large values in diagonal and low values in non-diagonal elements. So you could use actually the confusion matrix or normalized version of confusion matrix to get the idea of how your classifier performs on the data. So, and also the good news is that for confusion matrix, F1 score, precision, recall, AUC, and ROC, all of them, you could use all of them in scalar, and it is pretty easy. So maybe it is better to show you, for example, confusion matrix. In the scalar, you could actually see that there are lots of examples that you could see the confusion matrix without normalization or with normalization to see how much your classifier performs well on your data. So this is a 3 classes problem. Okay, I hope that in this last session you get some idea about the classification metrics. So at the end, maybe it is better to review very short about the regression matrix. So so this is for classification problems, F1 score, precision, recall. But if you have a regressor, for example, let's say you fit a model to some of your data, and you want to know whether your regressor is good or not. So we know that one of the performance measurements is mean squared error, or 1 over n sum of the difference squared, and another measurement is actually the mean absolute error, which is just yi minus yi hat. For actually regression, now it is enough to just know this, but we will see that in the deep learning part, in the third part of our videos, how what are the differences between MSA and MAE and how much they could affect on the model. And also we will see that they have actually different effects on the model. Okay, so I hope that you enjoyed from this part of the 100 days machine learning crash course, and hope to see you in the next part. So see you in the next part. Bye.